But last time we were talking, we had gotten into the temperature measurement side of things. Remember, there's 3 steps to our process of performing thermography. This is the second of 3. So, the first is we have the excitation or stimulation step. That is, we have to heat or cool the part that we're going to do. And then the next step is we have to gather the data, gather the temperatures, right? And then we have gathered the temperatures, then we are going to perform analysis. So this is kind of the details of that second step where we're gathering temperatures. And for temperature measurement, we were talking about infrared cameras and features of those. So array size, the resolution of it. So the camera I have here happens to be 464 by 348. So it has a total of 161,000 pixels. So it's essentially taking that 161,472 temperatures all simultaneously. That's known as radiometric data, or the actual temperatures. Some of our other cameras, the smaller cameras we have are 160 by 120, so they take 19,000, just over 19,000 temperatures simultaneously. And then how big of an area that's going to cover is going to be determined by the field of view, determined by the camera lens, as well as the distance that you are away from the part. And that's kind of the next thing we're going to look at today. And then finally, we have to keep in mind, based on that array size, the number of pixels, the field of view, and the distance, how far away we are, determines how big of an area each pixel is measuring. And from there, we can figure out what's the minimum size discontinuity that we're able to accurately measure. And we have to have an overlap of a minimum of 9, a 3 by 3 square, to confirm. And the reason, part of the reason for that is you can have a single pixel that's anomalous, right? If there is an error in the sensor in 1 pixel, you don't want to think that's a flaw, or have even worse, a single pixel that misses a flaw. And so you want to have confirmation by having that square area, that 3 by 3 area, being your minimum size. So how do we figure that out? That's kind of the next step here. So I've got an example, and this would be using this camera right here. The example, if we take our FLIR 95, it has a resolution of 464 by 348. Okay, lens field of view 24 by 18. So 464 pixels is the width, left to right, 348 pixels tall. Field of view 24 degrees left to right, 18 degrees top. So we're looking at it from the top. We're going to look at what the width of a single pixel is. Now, earlier we did look at on this camera, these pixels are square. The ratio between the resolution and the lens field of view is 4 to 3. If you divide, this 4 over 3, 4 over 3, and so that gives us square pixels. Some cameras, like our FLIR 1 Pros, we actually have rectangular pixels. The lens causes the pixels to become rectangular. And so you would have a different pixel width or height, depending on if you're looking at width or height, because they're going to be stretched one way more than the other. So you would have to do separate calculations. In this case, we can calculate the width of a pixel either width-wise or height-wise, and it's going to be the same because we have the same aspect ratio between the lens and the sensor. So if we look down from above, I'm going to say we're standing, if we look at 10 feet, what is the smallest discontinuity we can find? Anyone? No? No, just look at the slide. We're going to calculate it. And I encourage you to work through this with me. Any ideas what we do? This looks pretty similar to something else you may have done earlier in the semester. Where else did we look at field of view? With borescopes. And a lot of you all had to design an experiment to figure it out. Some of your experiments probably looked like this. Instead of a thermal camera, you'd have a borescope down here, right? Now you measured, a lot of people measured this, knew this distance and measured this and then figured out what this angle is. Now we know the angle and we know the distance, we're going to figure out the width. So the first thing we're going to do is split it so that we get a right triangle. We're going to look at 1/2 at a time. So 1/2 of our right triangle, and we're trying to find this distance x feet at the top, okay, half the width, which is 232 pixels, 10 feet away. What do we use if we have a triangle, a right triangle, where we know we know an angle and we know the opposite and the hypotenuse? What's that? Pythag, I'm not familiar with that one. Oh, Pythagorean theorem. Pythagorean theorem could tell us what the hypotenuse is, what this length is. We're trying to figure out, we only know one distance, but we know an angle. Trigonometry, what element of trigonometry? So which one is, we have, here's opposite over adjacent. Tangent, thank you. Tangent of our angle. Tangent of our angle equals opposite over adjacent. And that's in feet. Remember, this is feet, so our x, our distance, is going to be in feet. Okay. So we take the tangent of 12. We plug it in here where theta is. Right? So then x equals 10 times the tangent of 12. X equals what? About 2.13 feet. Okay. So half our triangle is going to be 2.13 feet. Now that goes to the whole side. How do we get the size of a pixel? Divide what? Divided by the number of pixels. How many pixels do we have? 2.13 divided by 232 gives us a pixel size of 0.009181 feet, or I've converted it to inches, just over 1/10 of an inch, roughly 1/10 of an inch. Okay? So what is the smallest discontinuity we can find at 10 feet, though? Is it 1/10 of an inch? You got a what? Yep, 3 by 3. So the width, there's my division there. I just moved it up a little bit. Minimum pixel overlap, 9 square, or 3 by 3. So we just take that pixel width, multiply it by 3. We get roughly 0.33 inches, right? So at 10 feet, with this camera, with this lens attached, we can accurately measure a discontinuity that's a minimum of 0.33 inches. That's not bad for standing 10 feet away. You know, and we're going to be measuring what area, how big of an area left to right are we going to be looking at while we're doing that. About just over 4 feet, 2.26 feet. So 4 feet, just over like 4 feet 3 inches, right? So that's a pretty good size area we're able to image at one time, as long as the discontinuities we're looking for are going to be over 33 inches, so or 1/3 of an inch, 0.33 inches. So if the allowable damage, say, is 0.5 inches, we could stand 10 feet away. If the allowable damage is only 1/4 of an inch, what would we have to do? We would have to move physically closer to the object we're imaging. So that's where it's important that we know the pixel size, because it figures out how far away we can stand, which directly affects how large of an area we can image simultaneously. So that's one of several critical items, the distance there, that we have to take into account. So for thermal imaging, the quality of the image is going to directly affect the ability it's going to have to provide you accurate information. And there are three main kind of attributes of an image that we cannot change or fix after it's been taken, short of retaking the image, fixing whatever the problem is and retaking it. So the acronym that's used is FORD, to help you remember it. And the first two letters stand for focus. So remember when I had the camera earlier, last time, I mentioned there's two ways we can focus. So a water bottle is a good thing to focus on. You can see here's my water bottle. You can see where the ice water is and where it's not. Okay. So that image right there now is in focus, which means we can accurately measure it. If it were to be blurry, you can see I can blur it different directions, right? That would not be a good image. It wouldn't be an image that we can use to take accurate measurements. So you want to make sure your image is in focus. We cannot refocus an image after the fact. Once it's been taken, you're stuck with whatever focus you have. Okay. The next, the R, is range. And this is not the scale that's on the image. A lot of people confuse scale and range. And what I mean by that is if I, again, look at my water bottle here. On the right side of the screen, you can see it goes from roughly 43 degrees at the coldest point in this image to 68.1 degrees on the right. That's the scale. That is not the range. Okay. The scale we can play with after the fact. In fact, right now it's set to auto. We can lock that in if we wanted to. And we can adjust it in the camera. We can adjust it in software after the fact. What the range is referring to is, on this camera, for instance, if I go into the settings, you can see there's a setting here for camera temperature range. And this camera is able to work in three different ranges. So -4 to 248 degrees, 32 to 1202 degrees, and this is all Fahrenheit. I have it set to Fahrenheit, and 572 to 2732. Okay. So if we're measuring things at room temperature, or a little bit colder, like the water bottle, we probably want to be in this top range right here. If you're going to be doing something a little warmer, like an engine or something like that, you may need to bump up to this, as long as you don't expect to get anything below the freezing temperature of water, below 32 degrees Fahrenheit. And if you're measuring some real warm stuff, you got to go to this one down here. Now, this camera has three different temperature range sensors in it. Not every camera does that. The little portable ones, the FLIR 1 Pros, those are a single range camera. Oops. So what I mean by that is that one, let me go back because I can't remember off the top of my head. The FLIR 1 Pro temperature range is at the bottom there, -20 degrees Celsius to 400 degrees Celsius. So that one, is made for kind of your standard temperatures, but it doesn't go up real high like this more expensive camera does. Okay, so focus we have to have, range, we have to have the correct range selected on the camera. We can't go back and change that later, because if you're in the wrong range, you're using sensors that can't image temperatures outside of that range. And then the last one is distance, the working distance. And that's what we calculated in the last step, is how far away are we standing. R is the lens. I say standing, but the camera could be mounted on a tripod. It could be mounted on a drone. There's all kinds of different platforms we can put these on. And so distance becomes important. We cannot zoom in on the image. You're all familiar, you've probably zoomed in on images on your cell phone, they get really grainy, right? You're not actually zooming in, all you're doing is making those pixels appear bigger on the screen. But it doesn't give you any more detail than what you had when you took the picture. The same thing applies with the thermal camera. zooming in on the completed image is not going to provide you any more detail. And you can't do like the CSI where you take the blurry image and have, have some computer guy enhance it for you real quick, right? And all of a sudden you can make out the person's face and run it through facial recognition and you know who the killer was in 30 seconds, right? Doesn't work like that. We can't find out what the damage looked like in 30 seconds from a bad picture. So focus, range, distance, all are keys that cannot be adjusted after the fact. The image attributes that can be are shown here. So parameters that can be set in the camera, they can also be adjusted in post-processing. These are controls that we can adjust in the camera, and they're ordered. I have them here in order of most important to least important. So the first one is emissivity. This is a scale of 0 to 1. And we have to compare it to a reference. This is how much on a given surface, the surface, and it's the surface treatment, it's of the infrared energy contacting a surface, how much of it is reflected compared to how much of it is emitted, how much of it is absorbed, and then it re-emits from the surface, right? We looked at absorption and emitting, and then we also looked at reflection. And in some cases, we have transference or transmission, like the lens on here is thermally transmissive. Okay? So emissivity is the most important thing. We have to measure that and figure out what it is for every surface that we're going to be measuring. Now, in order to do that, it's a comparative process, and we have to use a standard. And the most common standard that's used out there is simple electrical tape, and specifically 3M Super 33 brand has a known emissivity of 0.95. Other electrical tapes are pretty much all the same, but 3M tends to have higher standards than whatever generic stuff you picked up at the auto parts store. So that's what FLIR and Fluke and other thermal camera manufacturers recommend using. And what we do is put it on a surface, allow it to get to the same temperature as the surface, and then we can take an image of it and compare what our temperature reading is on the known emissivity surface tape to the area not right adjacent to it. And it can tell us, for instance, what we would be able to figure out is what's the emissivity of this gray paint on the wall here. And we'll do that in just a minute. Okay, other things, reflected temperature, how much infrared energy is bouncing around the room, is hitting that surface, and from all different angles. In order to do that, we use something called a diffuse reflector. This real high-tech item I got here is a piece of cardboard with some crumpled tin foil fastened over the top. Okay. I got a bunch of these. If you break them, they're really expensive to replace, right? But what this does by being a crumpled surface like this, is light or infrared energy. So tin foil is a very poor emitter. It's a great reflector of infrared energy. You ever wrap food in warm food in tin foil and it stays warm? That's not because it's an insulator, it's because it reflects that infrared energy back into your food. So this is going to reflect infrared energy, and by having it crumpled like this, it means it's going to take the heat coming off this light above me. It's going to take the heat coming off your bodies and bouncing off of it. It's going to take the heat from the projector over here bouncing off of it. And it's going to reflect it all different ways. And ideally, it's going to reflect kind of an average of everything towards the camera when you point the camera at it. So we use this to measure our reflected temperature. So we need to know that. Those two are the most critical. Humidity, relative humidity, how humid is it in the room? That you need a hygrometer to know. You can look at the outside humidity, but remember outdoor humidity, indoor relative humidity are going to be different. This time of year, it's going to be more humid it's going to be drier inside compared to outside because it's cold out. In the summer, it's typically going to be drier indoors because we're air conditioned. That's going to remove moisture from the air and cool it, where it's going to be hot and humid outside. So you can get a general idea. Most buildings are kept somewhere around 40 to 60% humidity. So if you don't know, just put 50% in, usually is what I do. Winter, you can bump it down to 40 or 30%. Atmospheric temperature, That's the air temperature using a thermometer, not using the thermal camera, because remember, the thermal camera has to be calibrated for this stuff. This is like a mercury thermometer or an alcohol thermometer. You guys all here, we had a bunch of mercury we found the other day. No. Yeah, we got it disposed of, but it was the temp sensor for the big oven down there. We replaced it. We pulled the thermometer out and turned out it was full of mercury. We didn't realize it. And then finally, object distance. And this is, we tell it how far away we are. This is that distance that you have to control by where your camera's at. But I wanted to keep the mercury, put it in a bottle and float a penny on it, but university says we have to get rid of it properly. A penny will float on mercury. You're not metal objects. But distance from the lens of the object, the camera, actually this camera has the ability to figure that out because it has a laser rangefinder in it. But if you don't, you can do that simply by doing a measurement. Uh-oh, what did I do? Try this again. So if we have our camera here, there's a little button at the bottom that looks like a laser. If I point it at something, press and hold that, you'll see there's a little laser symbol that comes up, tells me that wall's 22 feet away. 21 feet. If I release it, it goes away. Now you see, whenever it does that, the reason it gets a laser thing is it also does a spot. So it shows a little red spot what you're pointing it at, like a laser pointer. So that's the spot it's measuring to. Just looking at the wall, you can see like the support studs in the wall over there. Doesn't want to focus very well. There we go. See? You see the windows real cold in the corner. Okay. Okay. So object distance, we can use that spot sensor. Usually we just put it about what we're at. Now, the reason the distance is important is because the distance becomes the multiplier for relative humidity and atmospheric temperature. So when you're relatively close, the humidity in the air and the atmospheric temperature really don't have much of an effect. The further away you are, the greater the effect they have. So in our case, we're going to be, most of the stuff you're going to be measuring, you're going to be 3 feet away, 5 feet away, 10 feet away, 15 feet away. That's not very far. Where humidity and temperature, atmospheric temperature start to come into effect is when you're 50 feet away. And ask that side conversations kind of wind down. So the further away you are, the more that'll be effect. That's more for outdoor. Where you see that a lot is when you have things like imaging, like electrical transmission lines and substations where you don't want to get close to them. Or imaging like big storage tanks, like oil and fluid storage tanks and that kind of thing. So after acquiring the images, then we have to analyze them. And remember, there's two ways you can kind of directly view them, which is more of a qualitative measurement. It's also for larger discontinuities. It works well when you have what's called strong diffusivity contrast, if you're trying to look at different materials. So sometimes materials have a very similar diffusivity. Sometimes they're more they have a bigger contrast, and I can show you an example of a pretty strong contrast in a second. Water and ice, temperature. So, but they're not as sensitive to, remember those low aspect ratio where the diameter divided by the depth is less than 1? For those kind of things, you're probably going to have to use some kind of an actively analyzed, something where some kind of an analysis algorithm's been run on it. But, diffusion can cause blurriness. Oftentimes the discontinuities may appear a bit larger than they are, which, if you're erring on the side of saying something's larger than it is, it'll probably mean you're taking it out of service early versus late. Some would argue that's better. Some would argue over time that's worse because it's going to be more expensive that way. There's a human element open to human interpretation. Temperature variations or variations in reflectivity, opposite of emissivity, can cause false positives. And you have to view it over time. So oftentimes you want to take images over a period of time. So the other thing too is you want to be careful that emitted radiation rather than reflected radiation is being observed. And I'll show you what I mean. What I mean by that is, let me switch back over to this, and I'm just going to go out of, here we go. I'm going to go in here real quick and just show you an example of, so this is a steel bench top. And you can see there's a very strong diffusivity contrast between the black tape and the stainless steel surface. And the stainless steel surface is highly reflective, just like tinfoil is. So if we were to image this directly, you can see that this is the reflection of the infrared energy coming in through the windows. So you can see even here, this area appears much warmer than this area in between where the window frame is. But in actuality, this surface is all pretty much the same temperature because it's a bench top that's been sitting in a room. There is some infrared energy coming in, but honestly, it wasn't a super bright sunny day. That was just a day like today that's overcast. And you were getting some infrared energy, but it looks like a fairly large difference in temperature, but in actuality, there's very little difference in temperature between these two areas because it's not like it's in direct, strong sunlight. This is just the outdoor light showing. So what I mean by that is if I take a spot and put it here, you can see my spot here is 64.8 degrees. And my spot there is 61 degrees. So a little bit of a difference from that heat, but not much. But in actuality, it's probably not that much of a difference. It's just because of that reflectivity, we have to be aware of it. Now, this was an image to find the emissivity of this. So the emissivity of that is somewhere around what was it? Oops, I don't want the spot there. Here. The emissivity of that area was oops, not that one, this one here. Of the image was 0.69 because it's much more reflective than the tape, which is 0.95. So that's this last one where we want to make sure we're measuring emitted radiation rather than reflected. Okay? If we're going to do some kind of an active analysis, we're going to perform what's called signal processing on that. And that is we're going to compare not we, but rather a computer, an algorithm, machine learning, AI nowadays, is going to look at every single pixel and how does it compare to the pixels surrounding it. And there's different ways to look at it. It could be just, are we comparing it to the pixel above, below, left, right, and at each angle to it? Or are we comparing it over an area? There's all different ways of doing these comparisons. That's where those algorithms come into play. So these are used where you need repeatability. So it's got better repeatability, higher sensitivity. You can get more quantitative measurements. It can actually say, okay, there are exactly 10 pixels that show this much higher, this difference from the rest of the part. And each of those pixels is this size, so now we can get an exact measurement or a more exact measurement. So computers with infrared cameras typically is what's done. They make packages where this all comes together, or you can do it, with a camera plugged in like I have here. All kinds of different algorithms, from fairly simple to very, very complex, to detect things like those low aspect ratio discontinuities or cracks versus things like delamination. Or areas with very little diffusivity contrast. So I showed you an example there of very high diffusivity contrast. The type had a high diffusivity, the stainless steel surface had a low. An example of kind of the opposite of that is something where the diffusivities are very similar. And where is it? Here is an example of an image where the diffusivity of the tape and the diffusivity of the material are not very different at all. You can see the tape barely shows up in that image. And this is an MSX image. This is with the visual overlay. If I get rid of the visual overlay and only do thermal, you can see there's barely, nope, that's not a pure thermal image. Oh, that's right. That's not what I want. This is what I want. There we go. Here's the thermal only image. You can see there's almost no ability to see the difference between the tape and the surface. That tells me that the surface, the tape we know has an emissivity of 0.95. Because we can barely see the tape on that surface, that tells me that this surface is also approximately 0.95. This is the Snap-on toolbox. The red toolbox was down there. So here, if this was the image you were dealing with, and you were trying to find, like, if this was like a composite with that same paint on it, and you were trying to find damage to it, you may need to run it through some kind of a processing system in order to see things on it. What does it look like? Is something like this. So here's an image where we've had signal processing performed on it. So the top three images there are the same panel. This is a composite panel where images were taken. This was aluminum honeycomb with an epoxy graphite covering. Raw images on the top. Okay, this is a flash excitation technique. So 3 images were taken in quick succession after a flash of light that contained infrared energy. They were taken at 0.3 seconds, 0.64 seconds, and 1.28 seconds. So this is the raw image. This is what it would look like if we looked at it. You can see in this first one, obviously there's some stuff going on with these circles. We'll look at those in a minute, but some of the other details. This first one, what is that cross-hatching right there? What do we see there? That's what? Fiber orientation in the surface layer, right? Second one, we can't see much at all. There's a little bit of cross-hatching, and then we can still see some, some kind of features that are in the composite, that are in the layup. The third one, you can see we can start to see that honeycomb structure poke through. So that's the importance of taking images at different times if we're going to view them raw. But below, in this case, they ran an algorithm on the radiographic images called a first derivative thermographic signal reconstruction. I don't know the details of the algorithm. I'd have to go back and look at the paper, and it was lots of math that really isn't important for us. But what you can see here is it made that, so first off, in the first image, it made that fiber orientation stand out quite a bit more. And in the third image, it made, and even in the second image, you can see the honeycomb that you couldn't see before. And then it also brought out the various simulated flaws, especially in this third image right here, that weren't visible in the upper images, maybe just slightly in the 1.28 seconds above, but you can really see them down here on the bottom. So that's where the advantage of signal processing comes in. And often that's used with those flash of those, this again was a flash excitation technique. Barely a change in temperature in the material because it's just a flash bulb, just that little bit of warmth you feel. Maybe none of you guys remember this. Anyone ever played with old flash bulbs? All the time, yeah, okay. I'm that goofy of a kid, I guess. I still have old cameras that have the one-use flash bulb. You put a bulb in, you take the picture, the bulb burns out, like the bulb burns up when you flash with it. Aren't those what? No, it's a bunch of, oh, not that old. Not where you ignite the flash powder. We're not playing with gunpowder here. It's a bulb with a bunch of tiny fine filaments, sends a big pulse of current, and all the filaments burn up and flash. But that's kind of what they're doing here. But modern day, flash tube, like the strobes on the ends of a wingtip. If you go up to a wingtip, you turn the strobes on, old school flash tube strobes, you put your hand near it, you can feel a little bit of warmth come off of it. every time it flashes. That's the amount of heat that's being applied here. Okay. Here's another example. There's a raw infrared image on the left, and then a signal processed image on the right. In this case, this was a signal process where it was designed to bring out differences in diffusivity. So the damage causes more or less diffusivity in different areas. And so that's what this minimum to maximum, this is a diffusivity scale rather than a temperature scale over here on the right. How well the thermal energy transfers through the part. So I'm going to stop there from the lecture stand.